Okay, our next presentation today is from the Chemical and Materials Engineering Department, and it's titled Corrosion of Metallic Alloys in Airborne and Shipboard Turbine Environments. Sponsored by the Office of Naval Research, this project seeks to understand the fundamental corrosive effects of calcium-containing deposits that often pollute gas turbine engines in airplanes when in flight. To do this, the team applied thin films of calcium-containing compounds to metallic alloys and subjected them to high temperatures equivalent to when gas turbine engines are in operation. The resulting effects on the alloy were studied and observed to understand the corrosive effects. I now invite the Chemical and Materials Engineering team to the podium to share their presentation. Please.
Good afternoon, everyone. Thank you for joining us. We will be presenting our research on the corrosion of metallic alloys in airborne and shipboard turbine environments. My name is Harjot Singh.
And I'm Stephen Maldonado.
I'm Jenny Chen.
My name is Jack Webster.
And our principal investigator, as well as our advisor, is Dr. Vlupranar Ravi, and we're grateful for this opportunity to present our research on the behalf of the Chemical and Materials Engineering Department here at Cal Poly Pomona at the showcase. And we'd also like to acknowledge the following students for their contributions, as well as acknowledge the Office of Naval Research for their financial support. To give context to our research, the Navy employs a number of ships and aircraft around the world, and here on the left we see an example of a destroyer. In the center we have a aircraft carrier with a number of aircraft on board, as well as some aircraft in flight over the ocean. And these ships and aircraft are powered by gas turbine engines, which all operate at high temperatures. And so here we have a cross-sectional schematic of a gas turbine engine. And so we have a cold section and a hot section. And for the cold section, we have the air inlet, which passes through a number of turbines, which compresses the air before reaching the hot section, where the compressed air is then mixed with fuel prior to combustion, and the resulting expanding gases then pass through a second set of turbine blades for energy generation before exiting for propulsion. And I'd like to turn our attention to the turbines here in the hot section. And so here's a cross-section of a thermal barrier coated turbine blade, where we have on the far left here a superalloy substrate. Following that is our bond coat. After that is a thermally grown oxide, and finally a zirconia top coat. And the purpose of all these layers is to insulate the superalloy substrate from the hot gases produced by the combustion cycle. As you can see here, the blue line denotes the temperature profile across the cross-section. And so around the world, these ships and aircraft operate in all types of atmospheres, and these atmospheres can vary in pollutant composition depending on the region. And these pollutants can include alkali and alkaline sulfate salts, and in certain regions, the concentration of these pollutants is a lot higher, and thus can increase the risk of deposit-induced corrosion if ingested by the jet turbine. And so here's an example of a turbine blade before service and after a number of flight hours, where we see evidence of degradation, such as oxidation here, or adverse reactions with the environment, and also spallation, in which some portion of the surface flaked off. And finally, thermal mechanical fatigue cracks. And after analyzing the failed turbine components, it is indicative that the calcium-rich species play a role in the degradation, the multi-mechanistic degradation process you see here on the right. And these calcium-containing species can come from different sources, such as desert sands or from seawater, sorry.
Okay, so as due to the nature of the Navy's mission, the materials that make up these turbine blades have to go through mechanical stress, high temperatures, and a range of different austere environments. And in these environments, they have pollutants such as alkaline metals, sulfates and chlorides. And as the engine ingests these pollutants, they deposit onto the engine components, which could lead to corrosion. And among these constituents are calcium-containing compounds, whose role in the corrosion process is yet to be determined. And so what we want to understand is what what role this plays in the corrosion process at a fundamental level. So our overall objective is a fundamental study of the role of the calcium oxide and calcium sulfate in the hot corrosion mechanisms affecting nickel-based superalloys used in naval aircraft, as well as the Navy's shipboard gas turbine engines. So for our experimental approach, we control a number of different variables such as alloys, the salt film, the temperature at which we conduct these tests, the environment that is in, as well as the time, and the techniques such as immersion or electrochemical testing. And then after these tests, we do post-test characterization via electrical microscopy as well as optical, X-ray diffraction analysis, and mass change and recordings. So for our process, the first thing we do is create a mixture containing the calcium oxide or calcium sulfate, which is then deposited onto the specimen used via dropper to coat the top side, and which we then let dry. From there, we load it into the furnace for 50 hours at a temperature ranging from 900 to 1100 degrees Celsius, after which, after it's cooled down, we do post-test characterization.
All right, so moving on to our results. First, we'll start with our pure calcium sulfate deposit-induced corrosion. And these are just our cross-sectional images of our samples. And going from left to right, we have increasing chromium content of nickel 5, 10, and 18 chrome. And top to bottom, we have increasing temperature from 900 to 1,000 to 1,100 degrees Celsius. So just to orient us, let's take a look at our nickel 10 chrome at 1,000 degrees Celsius. So this mix of gray area is where our corrosion affected zone is, and the more uniform gray area is where our alloy is. So as a general trend, we can see that as we increase our chromium content from left to right, that our corrosion affected zone seems to decrease in thickness. However, as we increase our temperature from the top to bottom, our corrosion affected zone increases in thickness. So a conclusion we can make is that the chromium content does seem to help in reduce how corroded our samples are. So moving on, again, the same cross-sectional images, but this time colorized by which elements are present in a sample and where they are. So first off, we can see that in our samples, we have a nickel-rich external layer as represented by this bluish-greenish color at the top. Under that, we have a chromium-rich layer as seen with the bright green stripes. And we can also observe some internal sulfidation products with these orange dots in our sample. So now that we've looked at our pure calcium sulfate deposit-induced corrosion, we add sodium chloride into our salt mix. And again, our cross-sectional images in increasing chromium content from left to right, top to bottom, increasing temperature. And right away, we can see that as compared to our pure calcium sulfate deposits, that these samples have a much more complex morphology, and there doesn't seem to be a very clear trend in decreasing or increasing corrosion-affected thickness as we saw before. So from this, we can conclude that chromium content doesn't seem to have much of an effect, and the added sodium chloride seems to aid in increasing the corrosivity of our environment. Moving on, again, our elemental maps. And again, just to build off of how complex our morphology is, we can see that this time, rather than the more structured layers that we saw before, here we have a mixture of oxides. For example, in a nickel 18 chrome at 1,000 degrees Celsius, we can see that there's a mixture of white and green, which represents a mixture of our calcium and our chromium. And again, we can also observe internal sulfidation as represented again by these orange dots.
All right, so following post-test characterization of our alloys, we were able to identify a number of corrosion products that formed after our salt film tests. For our calcium sulfate deposit-induced corrosion test matrix, we can see that we have our phases and where they were detected in each of these micrographs pictured here. It should be noted that we have a three-layer structure of nickel oxide, calcium chromates, and chromium oxide forming across each of these specimens. As we increase the temperature, we're going to be seeing much more extensive sulfidation. This is due to an accelerated decomposition of calcium sulfate that happens above 950 degrees Celsius that leads to the formation of sulfur trioxide and calcium oxide. Once we introduce our sodium chloride into our salt film, we're going to see much more complex corrosion behavior as indicated by our mixed external scale here. And we also have formation of internal oxides and much more extensive sulfidation than what was previously seen. This is going to indicate that we have a rapid decomposition of our calcium sulfate and sodium chloride salt film, previously compared to what we had in our calcium sulfate standalone tests. The effective chromium content in these tests are also somewhat unclear. Okay, so using this as somewhat of a post-forensic analysis, we're able to use these micrographs to come up with preliminary mechanisms for how this corrosion is taking place. In our first case, where we have our calcium sulfate salt film applied to our binary model alloy, as we increase the temperature, we're going to see an inverse flux of our species going through our nickel oxide scale and then reacting with our chromium to form that calcium chromate scale that was seen, as well as some sulfates. Once we introduce sodium chloride, we can see that we have the formation of a two-phase film, liquid sodium chloride and calcium sulfate, that results in the formation of much more volatile species. And we're going to have a much more complex morphology forming, as seen here with our mixed scale, extensive sulfidation, and internal oxidation, and the formation of voids due to vacancy condensation and the presence of volatile oxychloride species. So to summarize what we found from these experiments, we can see that from the study of the effect of our calcium sulfate deposit-induced corrosion, for our calcium sulfate film, as we increase the test temperature, this is going to lead to a much more accelerated decomposition of calcium sulfate, linked to a thicker corrosion-affected area that can be protected against by increasing the chromium content. For our calcium sulfate and sodium chloride mixture, this formed a more corrosive environment under which we saw our mixed scales, and then the effect of chromium was not going to be as clear as in our calcium sulfate case. All in all, this is research in progress that we're going to be applying to a number of commercial experimental alloys under different exposure conditions. Now I'd like to thank you for your time and this opportunity for us to present on behalf of the Chemical and Materials Engineering Department. Many thanks.